So, good morning everyone. Thank you very much for making your way here on a Monday morning, relatively early by academic standards. I'm very happy to welcome Michael Roth, who has an interesting profession. He simulates weather and climate. Please correct me if climate is...
Sounds good so far.
For urban environments. And he has an education in engineering from the University of Waterloo and did a PhD in climate modeling at the University of Victoria. And we came into contact through a SOSIP project where we discussed how to best use reanalysis data. Those are global numerical weather prediction models that are run and forced to resemble observations through a simulation. And through this overlap, I figured it would be kind of nice to start a small stream in this data science seminar series that exposes people to, well, how do we use climate data, numerical weather prediction for all kinds of things that we take for granted in life. So I'm very happy that you could come today. Michael, I'll leave the floor to you, and I look forward to your presentation and to all of your questions later.
Very good. Thank you, Stefan. So,
good with the light?
Yeah, well, whatever's good for you, everyone. Can that look good? So, as you can see, what we're talking about today is modeling and data analysis for urban climates. So, my clients are architects, engineers, urban planners, people that are interested in the temperatures, the humidities, or whatever in cities or around cities, or frankly, in rural climates as well. So essentially everywhere. But at kind of a finer scale than typical. So we're really trying to get a sense of how does the temperature, humidity, whatever, solar radiation, how does that change all over the place? And often in places where we don't have MET stations. So, MET stations tend to be at airports. They tend to be in very specialized locations that aren't necessarily representative of the place that you're interested in either building or where you have agricultural or whatever. So we've developed a number of tools over the years to kind of give us a better picture of what those conditions are, and I'm just going to talk a little bit about that today. Should note, so I'm the top guy, this is Michael Roth, but we're a small, I call us a kind of a boutique engineering firm. There's two people, and we typically have a lot of co-op students to help us out, to do some of the nitty-gritty stuff. But it's kind of nice having two people. We can handle everything quite nicely, but we can't do a lot of stuff as much as we'd like to do. So anyway, a lot of the stuff you'll see it's a joint effort. So Marion was responsible for a lot of that work. So our motivation for what we do is to improve the urban microclimate. This is things like air quality, the thermal comfort of people. People walking around in cities. Are they getting blown over? Are they really, really cold? Are they really, really warm? For various locations around the world, this is a really important question. So this is our key. This is what pays the bills essentially for Climat. But our real motivation, this isn't what we always tell people, is something else entirely. So this is a map of the world, and it's showing the wet bulb temperature. I won't get too much into what wet bulb temperature is. It might be a little bit, we might be here, I could do a whole talk on what that actually is. But think of it as it's combining temperature and humidity, so levels together to give you a temperature. It's essentially the kind of the temperature. If our body cores are on around 37 degrees Celsius and our skin is around 35, so anything above that and we can't really keep cool. This is kind of, think of it as a 20-year return period on temperature all around the world. And what I'm going to do now is I'm going to screen those away for the ones that are greater than 35 degrees Celsius wet bulb. So these are locations, conceivably, you could go be outside and you could be measuring a 35 degrees Celsius wet bulb temperature. And why this is important is because if you're over 35 Celsius wet bulb, there's no way your body can shed the heat that you're generating. Just by, we're all like about a 100-watt light bulb. Think of it as that. So we have 100 watts that we're trying to shed all the time. And if we're dancing and doing other things, it's more than that. So if the ambient conditions are greater than 35, we've got a problem. And so some of these locations, in some pretty popular places like Dubai, in Qatar, in various locations in Australia, India, Iraq, even some places starting to percolate into Southern Europe, are conceivably could have a day or two that could be greater than 35 Celsius. So that's going to impact people, because people can die if they're exposed to that for an extended period of time. And it's not just, so this is based on today's return periods. If we start projecting this into the future, so here's just sort of a contour plot looking at the big one we're interested in is this guy here, this color here. So you can start seeing these colors start appearing as we start. The one on the left is a kind of a historical maximum wet bulb temperature you'd see. This is under maybe a global warming scenario that is sort of a mid-range scenario. And then we have one that's maybe a little bit more extreme. Still possible with the way our business as usual scenario. And we've got whole parts, this is the Middle East, we've got various locations that are going to see that more and more with climate change. So this is kind of a key thing. So what we're trying to do as we design our urban places or our buildings or whatever is we're trying to improve that. We're trying to shave away from that 35 Celsius. So what can we do as designers, urban planners, architects to improve that somewhat? The other thing is there's actually some very significant correlations between the ambient temperature, and how many people are going into hospitals. So that could be heart attacks, that could be any number of incidences of diabetes, or any number of heat-related things can happen just by looking at what the average temperature. And it turns out, for every location in the world, there's what we call a minimum mortality temperature. So this is an example is Netherlands, and it turns out 16 degrees Celsius is kind of a sweet spot for them. Okay? And as you shift kind of the left and right of that, or get cooler or warmer from that 16 Celsius, you start seeing more hospital visits. And it's kind of a hockey stick curve on the hot end. So as you get hotter, that increases quite rapidly. Okay? And it turns out, people tend to acclimatize. People like Canada, we're maybe used to, we can acclimatize to a much colder temperature than, say, someone in Singapore, where this whole curve might be shifted. But the key thing is, in that location, as you start getting a lot of variability in that temperature, which is something that we might see with climate change, we might start seeing heat waves that are going to be shifting us into here for an extended period of time, and then all of a sudden we start seeing more people making visits to the hospital. So it's not just, oh, it's hot outside and it's getting hotter. It impacts things like health and so forth. So this is always something we have in mind. And each location has a different number. So this is one for Beijing. Turns out it's on, I think it's on 21 degrees Celsius is kind of the minimum. But you can do the same thing all over the world. So you can see Toronto over there. I think it's around 20 Celsius. But at various locations, they all have this pickup. They all have this kind of a minimum location where it's kind of the optimal for that location.
Does that take into effect other impacts such as air quality? In Beijing, that's notorious for killing people off with the air, not with the heat. That's
right, but and that's actually a fantastic point. It's kind of a catch-all, this temperature, because often the temperature is correlated with air quality.
Right.
You know, so if you have a high temperature, sometimes you have more ozone, or so it's often there's a correlation between those two. But that's fantastic. So it's a fantastic question. It does bring that into account. The nice thing is all these things, so when we talk about temperature and mortality, it's about 3% increase in risk per degree Celsius. That seems to be a kind of common theme as you move around the world. But it's the same thing on water. It seems to be about a 3 degrees Celsius increase in temperature, or 3% increase in water consumption with temperature. And this is the same thing with energy. So, you know, you start turning on air conditioning as things get hotter, or you turn on heating as things get colder. These slopes all end up being around those three. It's kind of one of these weird serendipitous things that occur.
Do you expect if things get even hotter to increase more?
Well, this is sort of kind of a characteristic thing for a given location. So as things get warmer, the question is it kind of the boiling frog scenario? Are we going to get? Are we all just going to say, yeah, we can get used to this? So whereas 21 was fine now, 22 is fine. Okay. We get used to that. But there's some things that there's kind of a limit. Things like diabetes, you don't want too much heat.
I'm curious why at different locations around the world, the minimum risk comes at different temperatures. You would think that human physiology would be the same everywhere.
Well, yeah, it's interesting, but you think about places like Dubai, they're acclimatized for the desert conditions, right? If you visit these places, we come and, I teach in Barbados every year. So for the first 3 days, my students are just laughing continually because I am sweating. They think I'm dying, essentially. But then after about 3 days or maybe 4 days, I get used to it.
Too much rum.
Yeah, might be. That's very possible. So that actually has a, yeah.
I just was wondering why the curve is not symmetric. Like, why is it easier to deal with colder temperature?
Well, cold is interesting because what can you do in cold?
Yeah,
if you're too cold, what do you do?
Yeah, you get dressed, but don't you think that the energy consumption?
But energy is interesting because energy is, air conditioning is very expensive.
So it's not as efficient.
Yeah, and you have to, again, you have to add in more. It's like this is gigawatt hours. It's not some reduction in temperature. It's gigawatt hours, and you're going to need more energy for that air conditioning. It's more inefficient process. So that's why it's more of a sharp slope.
So does it hold true that this curve is always steeper on the warmer side than on the cooler side?
Typically, yeah. Typically. And we're highlighting that. We're not talking so much on the cold side. We are kind of highlighting because we are in sort of this scenario. There's places that are cooling, but there's places that are warming as well. And again, it's not so much the shift in climate, it's the definite occurrence, that return periods of extreme events are changing. Like that is the most important thing, frankly. The increase in temperature is one thing, but the increase in variability, I think, is the real danger. So that's kind of our background motivation of why we do a lot of things. So these architects, these engineers, these urban planners, some of the questions they've asked us are, you've got a grid layout of your streets, maybe they're east, west, north, south. Is that the best orientation? Maybe it's better to have a northeast, southwest orientation because you want maybe the sun to kind of shine down the street at certain times of the day, or you don't want the sun to shine down. If you're in Dubai, maybe you want to be shaded pretty much all the time. But maybe in a place like Ottawa, you might like to see the sun while you're downtown, as opposed to having these canyons that just prevent any of the sun getting down there. Things like wind. We want to, in some places, you have bad air quality. So you'd like wind to flush that stuff out of that city. It might getting produced in the city and it's not getting flushed out enough. What can we do to promote that airflow through the city? So we talk about the optimal shape of buildings. You know, should they be staggered? Should they be tall and slender, or they should be flat and squat? Just for wind benefits or for energy point of view. Impact of parks. This is probably the most interesting thing. Is you can, with our tools, you can calculate what is going to be the impact on the microclimate due to placing a park where there was no park, or what shape of that park should be. You can see how that park influences both people that are inside that park and kind of downstream of that park. So, you know, it improves the thermal comfort and maybe shaves away a little bit of that kind of extreme heat that some of these people might be exposed to. The other thing we do is we work with a lot of architects who are building these giant buildings that are like 800 meters high. I worked on Burj Khalifa many years ago. And this is a giant thing. What is the temperature and humidity and so on at such a high level? It's not the same as it is at the surface. It generally gets cooler as you get up. There's less moisture in the air as you get up. So how does that impact, you know, design of things like all these air conditioning units if the temperatures and the humidities are different? So we have to calculate those numbers somehow. And often to do all this stuff, we have to calculate, we have to generate what's called a weather file, which is essentially just a common delimited file of temperatures and humidities and solar information that you can feed into all these other tools that generate the energy usage of buildings and so forth. So we do an awful lot of generating these files for some of our clients. Plus, we like to do it. They often ask us, well, that's fine. You can do it for today. Well, what do you see it being in 2050? You know, what is going to be over the lifetime of our building? So, you know, we do work around the world. Here's an example in Chengdu in China, where we work with Skidmore, Owings & Merrill and a number of other clients to generate what should that configuration of buildings look like. In this location, the air quality is not so good. You know, you've got a lot of, you know, you've heard of China it can have poor air quality, and that's not necessarily because of all the industries. They have a lot of industry in China, but there's deserts upstream that bring particulate matter into it, so it's a bit of a perfect storm of air quality issues. And if you're in a place that's maybe in a valley, where it can't be flushed out as easily, it's really important to be able to encourage wind flow through your city. So we want to develop things where we develop channels that the air can kind of flow through. It doesn't get trapped anywhere in the city. So what we would do is we would put all this geometry into our model and figure out what the wind flow is going to be through the city. This one's interesting. This is in Sydney. You can probably recognize the bridge. Here, this is all ocean, and what we're interested here is what is the impact of these tall buildings swirling and generating an impact on a kind of a facility that was going in here that also had a bit of a marina. So there was some sailing going on here. And if you've got, you know, you're docking your boat, you don't want a lot of swirling winds as you're docking your boat. Any sailors in the room would know that. And so a lot of the work we were doing here is we were interested in what is the impact of these building upstream on the development we were working on and the marina that was associated with it.
You would do that at CFD?
Yes, yeah. So I'll be talking about that model in a sec. So again, this was another building. If you look here, this is actually an atrium that starts about halfway up the building and extends for 20 floors upwards, or 40 floors upwards. So the idea is, what are the conditions inside this atrium that's not starting at the ground floor, which would be fairly easy, but starting up here, and then, you know, heat rises, so it can get very hot, might get very hot at the top of the building. So what are the conditions within that atrium? The one I just sort of, I've been working on very recently is the Expo 2020 in Dubai. And here, so this is going to be, like Expo in Montreal, Expo. This is the Expo in 2020, and that's going to be in Dubai. Dubai is if anybody's been there, it's a very hot climate, desert-like climate. So what they're trying to do here is to provide kind of an oasis effect by shielding it with kind of a fabric. And you can sort of see what the idea here is. They're going to be able to illuminate that fabric with pictures, so they can watch movies and things like that underneath this fabric. So it looks like something like this underneath. So the question I'm asked by the architects are, what's it going to be like for the people that are walking around underneath here? So it's massively complex, because I have to figure out what is the impact of all these trees, this fountain, how much sun is actually going to get through that fabric. The fabric's going to get dirty because it is Dubai. There's a lot of dust, there can be a lot of dust in the air. It's already hot to begin with. So what can we do to kind of improve the experience for people in here? Because you can see there's a lot of people. This is many football fields wide, so it's a massive development. And just this gives you a sense of some of the results that we do. So this is City of London. You may recognize the gherkin, the pickle-shaped building. So just looking at the wind flow through what's a very densely packed, for London, very densely packed location. Medieval streets tend to be, all over the place in terms of there's no real grid system. It's just whatever organically formed over the many, many years. And so the idea is what we're trying to do is generate these nice maps that tell us, well, what is the climate going to be like in the various locations? So we might find that it's cooler or warmer than kind of a baseline condition. So if it's colder, this could be maybe if the wind is flowing a little bit too strongly. So wind tends to cool you down. Or it may not be seeing enough sun. So there may be overly shaded. So to do all this, we've developed a tool for urban climate simulation. So you're being data scientists. I'm talk a little bit of what that entails. So various steps, various things we need to do to be able to get to this idea of a perceived thermal climate. So that looks like something like, it kind of takes into account a number of things. So we're interested in what is the wind, because that can cool, or the wind can cool you down. So it can be, if you promote that, it can cool you down. What you're actually doing at the time. So if you're just walking around, it's different than if you're sitting, or you're running, or you're playing sports. The humidity, the air temperature. Obviously, those are two very, you think of the humidex, that combines these two parameters. And then radiation is probably one of the more important things. Us being in this room, we're going to feel the radiation from the lights and the radiation from the temperatures of all the walls and the floors around us. So we have to figure out what are those temperatures that are going to impact the human body. And obviously what you're wearing impacts that as well. As a designer, we don't really have too much impact on what people are wearing. Or really what they're doing. So in some places we're designing for a gymnasium. Obviously, we're going to be designing for people wearing shorts and running around. But for general, just outside, you've got a lot of activities that are possible. And there's a various number of ways you can measure this. You've probably heard of the humidex. This combines temperature and humidity. You may have heard of wind chill, and this combines temperature and wind. But to combine all of these, what we have are what's called a standard effective temperature, or a universal thermal climate index. We boil all these parameters down into one thing, and it's kind of like a perceived temperature. So it's kind of like a standardized way of, everybody's familiar with temperature means, but it's like, well, what happens if the walls are a little bit warmer? What does that do in terms of how you perceive the temperature? So if those walls are warmer, the perceived temperature is going to be warmer as well. So first thing we have to do is we have to bring in the urban form. So this is the computer-aided three-dimensional geometry and the landscaping associated with that. So it's things like, you can grab this information in a lot of places. So for instance, in Ottawa at Carleton Library, you can actually you can grab the three-dimensional geometry for Ottawa. And so all this is actual three-dimensional skinned with some kind of, like they've put the skin of the buildings on it. But this is all three-dimensional information that you can pull into your indoor model. But typically, cities like Toronto and Chicago are all getting this information and compiling this information and making it freely available for people. But there's a lot of people that are scanning around the world and generating all the data that they can. And then maybe they're extracting from satellites, trying to get that three-dimensional data, and then reselling it to people. So we work with Cyber City. We have an agreement with them to give us some information. But some of the stuff hasn't built yet, so that's where the architects come in. So they'll be design their building, and we'll have all the surrounding information. But maybe they're putting a new building in right here. It's going to be a 400-meter tower, and we'll have the geometry for that, and then we can sort of model what is going to be the influence of that tower going to be on the surrounding buildings. Another interesting thing now is, of course, we've got drones and LiDAR, so we can send a drone over this with LiDAR and actually get what is the three-dimensional structure of the city. And not even just what the three-dimensional structure is, what are the materials down there? So is it urban streets? Is it park? What have you? Because that's going to be influence what the conditions are. So essentially, it boils down to a kind of a cloud of triangles, right? We want to know what is the geometry, and all these it's just a cloud of triangles that we're going to feed into our process. And associated with all those triangles is am I a road? Am I a park? What are the heat capacities? What are the albedos, the reflectivity of all these items? Because all that's going to impact how the sun hits and flies through the city.
Just a question.
Yeah.
Looking at that map you have all over the city,
Yeah.
it strikes me that if you're out to, in quotes, optimize things for a particular location in a town, are there not some adverse effects in the immediate neighborhood or the close-by neighborhood that you have to deal with?
Absolutely, and this is an important thing to emphasize. There's a lot of, you can't just put a building of any shape into a city and say, yeah, that's what I'm going to do, and I'm going to optimize it for myself. No urban city is going to allow that, because you have to look at sight lines, and you have to look at shading. Like, are you stealing sunlight from the adjacent buildings? Are you making the wind? Are you creating canyon flows that are going to blow people off? Someone's walking down the road, right? So it's the same idea here. You have to get it approved, and to get it approved, you often have to do this sort of modeling. So any of the bigger cities have a fairly long list of things you have to show that you aren't adversely affecting your neighbors.
That doesn't always work.
What's that? No, you're absolutely right. Some people don't want it regardless, so they won't be willing to see any evidence. But sometimes, people are able to get things through that probably shouldn't have gone through. Yeah. Windmills or like wind turbines with no setbacks somehow can get built, or that can be a real problem. So essentially, we need to know what are the heat capacities, what are the albedos, and what forth of all these things. So we've got the information on what it looks like and what it's made out of. We also have to know what is the meteorological conditions. So if this is in Dubai, it's going to be a completely different situation than if it's in Ottawa. We need to know that meteorological thing. So this is where a massive amount of work goes into figuring out what is the typical conditions this building is being exposed to. So the typical hourly temperatures, humidities, so forth. So we want to know the hourly fluctuations in all these parameters. And we're going to throw that into our process and see what it tells us. And there's a lot of different sources for this information. So you can go to places like the US Department of Energy, and they have 2,100 locations where you can download this information. But 2,100 locations isn't actually there's a lot of holes around the world. And these 21 locations tend to be in places where there's already a lot of stuff built. So a lot of stuff in the United States, a lot of stuff in Europe, but really not much in Africa or Australia or whatever. So this is one source. NOAA provides free data around the world. But again, this looks like a lot, but many of these stations may have been recording for 1 hour and then they shut off, they were never heard from again. It's rare that you have a meteorological station that operates over an extended period of time. And it's really discouraging when you look at something like Africa, where you'll see something come up for maybe a year and you go, okay, great, and then it just dies away because they've lost funding or there's been a war or any number of things. Africa it's awful in terms of the conditions. So what we often turn to, and I think Stefan alluded to this earlier, is the idea of this reanalysis data. So, and I think you described what it was really quite well. It's the idea that we're going to take all the things we know about the atmosphere, so all these stations, so things like all these stations, we're going to combine that with satellite data. So we're constantly measuring, we're beaming down radiance, and we're grabbing it back again and measuring how that gets affected as we go through the atmosphere. So we get a sense of what's in there. Is there aerosols, is whatever? And we use all this information and we try to combine it together so we get a consistent picture of the atmosphere everywhere. So it doesn't matter if you're in Nigeria or whatever, we've got a consistent picture that combines all this information into kind of a gridded product. And once we've got that, we've got each one of these represents an hour. We can actually go to one of these locations and pull out that time series that I was interested in. So we go to the same location in all these pictures and we generate a time series. Yeah.
So is that data set proprietary for you?
Nope.
It's public?
Yep. So this is an example. This one is CFSR or CFS-V2. So this is from NCEP in the States. A lot of these come from the States, but some come from Europe. Just like there's global climate models from all around the world, there are reanalysis products from all around the world. So you can, typically they're free to download and do with what you will. Some of them may have a little bit more of a commercial. You can't really be using it for commercial purposes. So some of those we have to shy away from or get special permission to use them. But these are a fantastic resource to use. Now they look like they're pretty high resolution. You know, you've got a lot of detail here. But when you start drilling them down, you find out that they're actually on the order of maybe 30 kilometers. You know, here's a summary of some of them. We've got from the various organizations, the European Center for Medium Range Weather Forecasting, the top two. NCEP is like the NOAA. Think of it as the NOAA version. And NASA has recently come up with the MIRA-2 data set. All these are fantastic, but they generally range from 30 to 70 kilometers or so in terms of horizontal resolution. And that sounds pretty good, and it is pretty good. You know, you get pretty good, that'll give you a pretty good picture. But depending where you are, you could be along a coastline, and one of these, you want to pull at a grid point, and it's actually right over the water. And if you were to go 1 kilometer in, it's going to be actually a completely different microclimate. So we have to figure out how do we translate these actual grid points to the place we're actually interested in.
I've often seen the advertisements for weather stations which you can buy and
Yep.
put in your backyard.
Yep.
for a project, is it feasible to populate an area with these things and use that, or is it, I mean, it doesn't give you any history, but can it give you a current?
Yeah, I can talk about that right now, actually. So this is Barbados, and so maybe these 4 points are those grid. So this is the nearest grid, and we're interested in this location. What you can do is, yeah, you could put a Met station or weather station in there, and you maybe only need to do it for about a year or so. And then you can sort of figure out how does that correlate with your reanalysis data. So you build up kind of a very simple, it could be just a simple linear regression between the temperature you're seeing in your observational site, like this Met station that you've bought, and what is it against the reanalysis data. And then once you figure out that model, then you can use that reanalysis data to back calculate what your Met station would have calculated over all the other years. But yeah, I've got a Met station in my backyard that I do the same thing, you know. Yeah. So yeah, this is the idea here is you've got this reanalysis data. It's fantastic. It goes back to the 1970s. It's continuous. It's every hour. You know, no Met station is every hour. There's maybe a few in the world that have been able to keep it up because they've got redundancies or so forth. But reanalysis data is continuous, complete, everywhere. So it's fantastic that way. But again, it's not as high resolution as you'd like. Some of them, this is the island of Barbados. You might have dots that are only one of them might actually be over the land. So you might say, well, okay, I'll just use that one. So that would be the simplest. That would be kind of nearest neighbor interpolation. You might just interpolate between those four. And that might be better. Actually, and it might be worse. You have to kind of evaluate. So how do we get from these 4 points to here? The other thing you might have is there's an airport here. So can we use the airport information to help with the reanalysis? Because that's measured ground truth data, right? That's going to be what's there. The reanalysis maybe has some of that information in it, but it's maybe has some biases. So we can kind of use that information to bias correct that reanalysis data. So there's a massive amount of literature going in right this moment to figure out how to bring all this information together. So there's all sorts of downscaling methodology to figure out what is the best way of calculating that condition. So Barbados doesn't have a lot of topography difference. It's not that mountainous, but you know there's going to be terrain. The effect of terrain is significant impact on temperature. So as you go up, the temperature decreases. So we can actually use that information to kind of modify what that. We don't just do simple interpolation. Maybe we interpolate after we've lowered everything to sea level, interpolate, and then we bring it back to the location we're interested in. So we can use things like terrain to help us interpolate. We can use things like, this is a satellite picture of land surface temperature. So can we use, could be 30 centimeters in resolution. Can we use that information to help us interpolate the reanalysis data down to a finer scale? So there's various techniques that we use to do that as well. So this is all form of statistically. This is just using some sort of predictor, what we call, or some kind of information to help us increase the resolution of that reanalysis data. Get it down from 30 kilometers, maybe get it down to 1 kilometer or even 100 meters. The other thing we can do is use what we call dynamical downscaling. So this is maybe a reanalysis data set. So off the coast, this is San Francisco. So this is the ocean, and Google's here, and you know the city of San Francisco and so this is what the picture would look like if you just looked at it from a reanalysis point of view. So pretty blocky, you know. This is a low resolution bitmap. So what you can do is you can feed that information into a higher resolution numerical weather model to get it down to a much smaller scale. So this is going from, say, around a 30 kilometer scale down to a 4 kilometer scale. And what it allows you to do is take that information and really refine, so you can see that the impact of the ocean versus places like urban centers. The area is so built up in here, all the industries, the Apples and the Googles and the so forth, Silicon Valley area. There's a lot of heat in that being generated there. So this is a technique we've kind of, this is used by a lot of people. We've created a methodology to do this kind of for the purposes of creating timescales or time series data. And we've also put a lot of the information. We're going to be providing this for free. Eventually, these weather files using reanalysis, we're going to make this available freely for people to download. So that was the meteorological part. We also have to figure out solar. So we have to figure out how solar works throughout the, how are we doing for time here? I don't want to bore or go too long.
40 minutes.
Yeah, okay. So what we're interested in here is trying to figure out how well exposed are we if we're on a street here or we're on a park or something, how much of the sky do we see at a given location. So you may have heard of a fisheye lens. So this is trying to give you a picture looking up, try to see the whole sky at once. So these pictures are kind of a fisheye view looking up for various locations around the site. And with this information, we can see if you can see more of the sky, you can see more of the sky. The sky can be at night. It can be cold, and you're gonna be radiating into space. Perhaps you're gonna feel cold. But if it's all the buildings are enclosed, you can't radiate as efficiently with space. You don't get as cold. It's like the impact of clouds. So we have to figure out for all these locations. We have to figure out how much sun we're getting at every single hour of the day. Yeah.
If I can just jump in, for your radiation balance in the urban canyons, do you use a full radiosity approach with like multiple reflections and everything?
We do now. This is a little older, but yeah, our latest version does do that. Yeah. Yeah, and that's actually the most expensive part of the calculation. Yeah. So yeah, so what he's talking about is we want to, if we've got the sun hitting at a certain time, it's hitting a bit of the building, it reflects off, hits another building, so forth, so forth. All these photons are bouncing all over the place, heating various elements more than heating other. We have to keep track of that somehow. We have to figure out what is the surface temperature for every hour of the day everywhere in this picture. So it's a massively it's a massive calculation to do. So we use what's called the discrete ordnance model to do that, but won't go into the details of that. And then finally we have to do the wind. We have to figure out what the wind's going on. So we use what's called computational fluid dynamics, which is just we grid this whole domain up with cubes and squares and so forth, cells, where we're going to be storing the wind, the temperature, whatever. In the middle of all these little cells, we're going to have more resolution where there's more geometry. And we're going to do Newton's second law, looking at the conservation of momentum, trying to figure out what the wind is through this grid. It's a full three-dimensional thing, so we're modeling a three-dimensional wind flow for all the wind directions around the rows. And so so for example, if the wind is coming from the upper right, you get all this swirling information colored by velocity. So you can see channeling. You can see areas that are maybe a little bit more stagnant, where it's bluer is lower velocity. The greens and the reds are higher velocity. So you can see some real high velocity locations in some places. But it's all like a stream flowing through this thing. We typically, for every hour we do kind of a steady state simulation. So it's kind of like a snapshot in time and we solve it for that. That's really not what's going on, right? You walk outside, you don't have a steady state flow. You get bursts and gusts. So we've been moving a lot more to, right now we'd be solving more of an average. We have a kind of an average picture of that turbulence. So we model the turbulence, but it's an average picture of it. Really what we'd like to do is we like to be able to model these eddies as it goes. So this is what we call large eddy simulation. We're actually tracking this within that hour. We're tracking the change in velocity and size. So you get much more complicated picture. So it looks more like this. So this, you're tracking eddies that get detached. I know there's one that constantly being formed. This is going to change the perceived comfort, the thermal comfort of individuals as they're walking through the city. This is massively an order of magnitude more expensive to calculate than just assuming a steady state solution. And this is why, I think you referred to using IBM. So we have access to the Blue Gene thing, Blue Gene supercomputers, trying to take our processes and putting them on IBM's Blue Gene, see if we can build something that can do this. Combining all the things, the solar radiation modeling, the wind, everything all into one package.
So when you do that modeling, do you look at all historic wind directions in that particular area?
Mm-hmm.
So you can actually have a full 360 view?
That's right.
Do you just have a big circle and put it on the boundary conditions?
Yeah, it's a square, but yeah, it could be a circle. It just turns out numerically it's easier just to have a square and then set the boundary conditions that way. But yeah, it could be a circle. I've played with a circle, but it tends to be a little bit more unstable for some reason.
So what about the geology of the situation?
You mean like the terrain?
Yeah, as opposed to the buildings. The buildings are an add-on, so do you have a base?
Yeah, so typically we'll have a topography that we've, like the elevational changes, which can be very important in a lot of locations. So yeah, you can model this without the buildings and get some quite interesting flow. My business partner is actually interested in doing like sand drifting, like his PhD was in sand drifting and snow drift modeling, and it was more of a terrain, how the dunes form and that sort of thing. So he loves the terrain bit, and then we just sort of plop the buildings on top of the terrain.
If you average that picture over time, do you get something like your steady state?
Hopefully. Hopefully. Not always, but hopefully. Something close.
Time and direction. Where would you not want to live?
Well, you can say, again, it's like climate change. Sometimes it's not so much, you can get used to if it's this sort of a steady flow, but if you're here and you're constantly being hit by the shedding vortices off a building, that's maybe not so good. Gustiness isn't what you really, that's not going to lead to thermal comfort if you blows your newspaper away while you're sitting in a park. And finally, probably the biggest thing that we have to do is figure out what is the ground temperature at any one time. So we have the solar shading, and that we want to figure out how does the temperature change at the ground for every hour. And for this, we have to kind of do the balance of all the fluxes of energy that are hitting that surface. And what is that surface? So if it's grass, we have to think about how much is evaporating off that grass, because that's going to provide some cooling to the surface. So if it's a wet surface, the minute it evaporates, you're taking heat out of that surface. It's keeping it cool or moderating it, versus if it was just pavement, the pavements can't shed heat by sweating. We shed heat by sweating. The grass can shed heat by sweating, but pavement cannot shed heat by sweating. It has to do it by getting hotter and hotter and hotter so that it can shed it with radiation. So we have to figure out that surface energy balance to be able to get what that ground temperature is. So this is where the designer has this is what we call the design dials. So this is what he can do. He can choose things that have high albedo, so they have high reflectivity. So things that are white, maybe white surfaces, or have a different texture to them so that they reflect more radiation than others. So this can lead to improvement on things like urban heat island and so forth. High heat capacity materials, they are going to absorb, cities are made with things that have high heat capacity, unfortunately. So the concretes, the cements, and that sort of thing have a high heat capacity. So they store all that energy throughout the day, and then they release it at night. So you get a much smaller diurnal or daily change in temperature in a city than you get in the rural. It just can't shed the heat as fast during the day. But the minute you put vegetation into the picture, as I said, now you've got another mechanism of getting rid of heat. You've got this latent heat transfer you can do, and that provides a great radiational cooling. And you put trees up, that shades the surface. You don't have as much sun hitting it. And being in the city, we have all these air conditioning units, they're shedding heat. They're constantly rejecting heat into the atmosphere. The people, the cars. Water features, they provide, again, that's like they're sweating. All the energy coming from the sun is going into evaporating water, as opposed to heating the water, it just evaporates, and that provides cooling. It leads to increase in humidity, but it's a cooling effect. So just, we can do this modeling and we can see the impact. If we look at the red line, that's the actual surface temperature on the top over asphalt and on the bottom over grass. So it's the same, all we're doing is changing that surface from asphalt to grass, and we see a much significant reduction in the temperature of that grass versus the asphalt. And if I'm walking over grass, I'm feeling the temperature of the grass that's much lower, I'm going to feel much more comfort than if I'm walking over a hot beach or a hot asphalt surface. And trees are even better because now I'm looking up, I can't even see the sun, so I'm not getting that warmth from the sun, so I'm going to feel much colder. The ground is much colder, and I'm not getting the surface effect of the sun. It's going to really significantly reduce or improve my thermal comfort.
So if we look at construction, urban construction these days, there are more and more buildings covered in glass.
Yeah. Yeah.
What's your observations there?
Well, glass is a engineer's nightmare. Architects love it, but glass has come a long way from the old days of single double. It's not just single double pane anymore. There's a lot of coatings and a lot of fancy things you can do with dimples, or it can react to sunlight, so you can change the shading for various times of the day, make it react to the sunlight. So it's not as bad, but typically glass you want to reduce, and for our environment at least, you want to reduce it as much as possible, unless you're trying to provide for passive solar, to heat your building from the sun during the winter. And then, but there's also, that's probably 90% of figuring out for energy of buildings in Canada is what can I do to both stop and encourage sunlight into my building. So glass is a major part of the design of the building. And plus it reflects too. So you get these, you may have heard of the walkie-talkie building in London. So this is this building that's shaped, it's kind of shaped like this. So it's kind of lots, it's all windows, in a short little canyon, but they've had expensive cars parked here, and the sunlight comes here, and it's like a mirror focusing on this poor guy who parked right at the focal point of the mirror. And they've had cases where the cars have melted, like the paint has peeled from parking, so they've had issues. And it's actually a bad one for wind as well. Yeah. So the walkie-talkie building in London is a famous example of glare that you can get off these windows. And again, this is another thing that the top architects will design for. They will do the modeling to figure out the glare off of the building and its impact on the surrounding buildings.
Bring up an interesting point.
Yeah.
Presume that you folks work on a fee-for-service basis, somebody's paying you to do
Yep.
something, and that somebody's having something to do with building a building.
Yep.
What's the risk of you ever being sued?
Typically, we're limited by our fee. Plus, we have errors and omission insurance. But for the most part, our risk is fairly low. Yeah, we're at the end of the food chain, so we're the consultant. We come in maybe at the beginning, and it never gets built like the way we suggest it should get built. In the second, because things get value engineered out and that sort of thing. But typically, it's based on whatever fee we're charged. But we've never had any problem. Let's put it that way. Knock on wood. Never any wood in these buildings anymore. Underneath? Some. But anyway, it's a question that keeps me up at night. Because I used to do life safety type stuff. So I did Chicago Union, what happens if there's a large fire and at Toronto Union. Like what if there's a large fire? So I had to model that. So that one keeps me up at night. So I sometimes check the news and so it's all about generating these maps, heat maps around. So we can before we're involved and we put parks in, we encourage the wind flow through the thing, you can actually see some fairly significant decreases in that temperature just by changing the materials, changing the widths of the tree, the shape of the buildings, encouraging more wind flow. You can see a very significant increase in the perceived comfort of that site. Okay, so it doesn't really look that much different, but there are some minor things that we've done to improve the matters. Different materials, different shapes to some of the buildings, and so forth.
Is that an actual location? No.
So what if, right?
This one, I forget where this is. I've seen so many of these. It's kind of like a Rorschach for me now. This one doesn't give me any sense of anger or anything. So this one wasn't a bad one experience. So typically they're in China. We do a lot in China, but the fact is 38 tells me maybe it's in the Middle East somewhere in Dubai. But this looks like a coastline. This actually might be Chicago? I'd have to look at it a little bit more. I don't want to lead you astray. But anyway, the point of the matter is, through this modeling, we can really show, we hate to use the word optimize, but we can kind of move from the baseline and start adding in more vegetation, changing the configuration, and maybe really significantly improving the comfort levels for the people in that environment. So this thing has a lot of moving pieces. So wasn't quite sure about the background of the people here. So I've been, this is bits and pieces of my work. Sometimes, originally it's like, this is just me I've got 4 Amazon instances going and they're all running. It felt like kind of a bit of a short-ordered cook where I've got a mazillion different cases I'm running, of different scenarios. So I'm solving for various things. So we've actually put this on we partner with people called Parallel Works, and we put this whole configuration on a high-performance computing platform where they can kind of upload, so an architect could use this where they can kind of upload their geometry, upload some configuration files, and hit execute, and they'll get all these heat things back. And so this is something that's even useful for us if we're doing the analysis itself, because they can look after all the computational bits and we can just sort of focus on the consulting. And ideally, we'd like to make the process, we like to make that open source. We tend to be, we like to be an open source type person, but right now mostly it's just our clients are using this, like the architects themselves. Yeah.
So for an architect, when they upload a model, I know often when you do analyses on it, you have to kind of dumb down the model.
Yeah.
So do you often have to remodel what they give you, and what kind of file formats are you working with?
Right. So you're an architect? Okay. Yeah. So we we've been working a lot about trying to export directly from the architect's software. So if you use Rhino or any of the other ones, you know, exporting it right from that and then hopefully getting the pictures back in whatever they're working in. So our, you know, SOM and that, they like to use Rhino, so we work a lot with them. So that's probably what we would do first. But so they would never see this picture, because even this is kind of, it's too much information. You know, you just want to be able to get right out of the software you're designing in and get that geometry back in. So, but in terms of the, you know, often we have to do a little bit of cleanup ourselves to the models. It doesn't have to be watertight, but it has to be, maybe more wind tight. So maybe things overlap so that the wind can't get inside the building type thing, and then spend all this time trying to figure out solving the wind inside the building, which really is what we're interested in. So, but yeah, it can be frustrating that way. You have to, oh, now I have to close all this stuff off. And
with some of like the larger urban landscapes that you're working with that you get from like the Carleton University, if they have a model of the city, I know that oftentimes the data isn't very accurate, so how do you go in and then verify that data? And do you work with like the materials? Because sometimes the materials aren't applied properly, so you have to put all materials.
Well, it's kind of like we have to make sure around, you know, far away, it doesn't matter so much. It doesn't have to be perfect, you know. But as we start getting closer, we have to get a better sense of making sure that it is pretty much. So we rely a lot on the architects themselves saying, yeah, this, you know, the immediate surrounding buildings, yeah, we're pretty confident in that. And our building, yeah, we can give you the information. Or these are the things that we want to try. So we want to try these glasses and these concretes or whatever. So yeah. So you know, there's a lot of moving pieces. So we have to fit, the meteorological thing is probably where we spend a lot of our time trying to just boil in all the massive terabytes of data. It's not big for you guys, you know, you're big data. We're maybe medium data, but we generate a lot of data. So, you know, the process of doing all this wind flow analysis for every hour of the year for a big giant many million cell model, that's a lot of data that we generally use, and then a lot of it we end up throwing away, because we're just distilling it, because it's easier, we find, to recalculate things than to store the data. It's just too much. It's too much data. So it'd be interesting. I don't know if there's any, you know, who here is actually doing a lot of generating data or knows a lot about databases, or is there a experience that way? Because one of the things, you know, we have is we take these reanalysis data sets come in grids, and they're kind of horizontal grid that we have to, we're maybe only interested in one part of that grid, but we're interested in every point, every slice of that grid. So we're only interested in one location, but we have to sift through every single grid to get to that point. So it's the problem of transposing data for us, where we're not interested in the horizontal slice, we're interested in the time series, that other dimension. So how do you best store the data or transform the data so that you can get those time series out very quickly? That can be just generating the data in a proper format is where we spend 99% of our time these days. So it'd be interesting to hear from you, the experts, what kind of software you use. I use HDF. I don't know if that's meaningful to anyone here, to store these big three-dimensional matrices. But what do you know in terms of databases for storing, you know, it's essentially just 3D data that I'm interested in typically one axis of that data. And it comes in the wrong axis. It's stored in the wrong axis. So, what else? If anybody's been doing any downscaling, I'd love to talk to you about that, because that's another thing that we do a lot of. But other than that, I don't want to go too long, because I think I've already gone longer than I should have. So other than that, is there questions you had? Hopefully, yeah.
That would be quite interesting. Wanted to know if you'd worked in any really windy places like Chicago,
Yep.
Portland, Maine, and Winnipeg, or Pincher Creek, Alberta.
Well, never. We don't do hardly any work in Canada.
Oh, okay.
Yeah. So Chicago, we do a lot of work in. Yeah, and not necessarily for the work in the city itself, but for our clients are all in Chicago. So a lot of the top architects are in Chicago, New York, or Boston. So that's where a lot of our.
So no models for Portland, Maine, and Winnipeg.
Yeah, I've never done Portage, Maine. I know, but no, I haven't done that. But Chicago, yeah, Chicago, the Canyon, the Windy City is yeah. It's great that the architects live there because they're constantly being exposed to extremes of temperature, extremes of wind. So it's a great place for architects to live.
Extremes of politics.
Yeah, that's right. Yeah. So but New York is another place where there's all this interesting architecture going up, and so.
But interesting in your operational model, at the beginning you mentioned there were just a couple of you and you relied on co-op students for your cheap labor.
Yep. Yeah, and frankly, I end up.
Operational for you, I mean.
Yeah. You end up doing things like we don't code elegantly. You know, we just struggle to get it done in time. So it's a lot of Python scripts and a lot of stitching things together, making it work with a hammer, and then it doesn't look pretty sometimes. But it works, hopefully.
The students you hire come from which areas?
I'm from Guelph. I'm an adjunct at Guelph, so typically from Guelph. But yeah. We've got a relationship with Western for this SOSHIP program. So the partner in that is got students, and we've been using them as well.
Which disciplines?
They're comp sci or mech eng. It's the wind tunnel. There's the wind. I don't know if anybody knows the wind tunnel at Western.
Right.
Yeah, there's a really beautiful one, a new one that's shaped like an octagon. So you can do tornadoes. So you can there's fans on the outside of the wind tunnel and a fan in the middle, so you can actually do downbursts and tornadoes and swirl things around, do all sorts of neat things. But you can see it if you ever drive down the 401. You can see the building as from the 401 looking towards London. You can actually see this building. It actually looks like a temple because it's like an octagon shape and it's got a dome. So you think it might be a religious site, but it's a wind tunnel. So.
I'm wondering, the simulations you do, they're fairly specialized and involved.
Yeah.
And let's say in science, as a reviewer and editor of publications, we've pretty much hit a limit in our ability to figure out if what people present is even realistic.
Yeah.
And I mean, I produce a lot of software myself and with students. And there are, of course, a number of good methods out there to ascertain that your software is good.
Mm-hmm.
Typically, unless you're Microsoft or Apple, you don't have the resources to implement all of this.
Right,
A lot of stuff
right.
gets done on the fly. So when you simulate something, let's say for a city, for someone to get a permit, who's checking a simulation? I mean, for instance, I could be in engineering, I could be an architectural company that says, well, let's just divide certain of those runs. Let's divide the initial wind speed by 7.5, and then let's do it again. And there will probably only be 3 people on the planet who look at that simulation and look at your description of what you do and say, nah, I don't believe that.
Mm-hmm.
So have we reached the limit of even using this type of work reliably?
Well, the great thing of all this is, it's the same with global climate models. People have been talking about how the uncertainty has increased with global climate models. Well, it's because they've gone more complex. They have vegetation models, they have economic models built into these things now. So there's more of a global space they're exploring. So there's possibilities that the climate model can allow. And we're adding more complexity to ours as well. But I will say that what we're getting more and more interested in doing and working with people is actually censoring up cities. So I know my business partner a lot more has interest in building little sensors and working with people to put sensors throughout their city so that we can run our model and see how ground truth it is. So yeah, otherwise it's a leap of faith, it's useless. But the other thing I'll note too is we're not necessarily looking at on October 10th, 4 p.m., is it going to be this? We look at averages, just like climate models, we look at averages, and also are the colors changing? So we're looking at relative changes as well. So we look for improvements, we don't look at absolutes as much. We're trying not to. So we don't say it's going to be 35 Celsius, we say it's going to be, 3 to 5 Celsius better. So.
If you're working with a architectural as a client, how long typically does your engagement with them last to deliver the product?
Mm-hmm. Well, it depends. If we just want to assess really quickly, it could be in a design charrette. Maybe someone does. We have initial design, and we can put it in this, and this takes an hour or so, ideally. But typically, it's maybe more in the week. You know, they give us some ideas, and we go run it, and we come back and we talk about it in a week. But theoretically, there's nothing. This process here takes an hour or so, because it's multi-processes, and throw the power computers at it. But sometimes I just run it on. I have a little 8-core in the basement that I run, and I'll do it on that.
But it's not months.
No. Well, sometimes it's drawn out, right? Because it's the architectural process. We're a small little bit of it, and they have a hurry up go because we've got a deliverable that's due next week, and so we do something, and then we don't talk too much, and then the next deliverable comes, and we might do a whole bunch of work right before that. So it could be a drawn out process, but our involvement might just be kind of commando missions, as they need us. We come in joint task force 2, and we come in and parachute in and help.
Do you, I know you're a two-person firm, so you don't have a lot of spare time, but do you somehow associate with international groups where people doing similar work, and you tackle common problems and or lobby for things or whatever? Is there anything international? Because I'm asking this from the perspective of CODATA, which is kind of an international group pushing for improvements in data and research and so on.
Well, we're not the only ones who can do this sort of thing. We maybe do it a little differently. I'm not going to say we do it better, but there's other firms can do this, and bigger firms.
My point was,
yeah.
You work with other firms collectively to improve the situation for everybody.
The only thing we would typically do is either we open source stuff, or we attend conferences. Like a big one for us is the International Conference on Urban Climate. Happens every 2 years or so. So we'll go and we'll present there, and we'll talk to the people there and say, oh, what are you working on? And this is what we found, and that sort of. But it's kind of like how academia would work anywhere. It's we don't get involved with any kind of like common data format type organizations and that sort of thing. No. But that would be nice for, if we wanted to go from transposing data really quickly, if there was a way of doing that. So talk about different ways of doing that. That would be great. But no, we don't do anything with those type of organizations. You get a...
Yeah, I guess it's more of a comment. Thanks so much.
Yeah, hopefully you got something out of it, yeah.
My world has been the city of Ottawa.
Yeah.
For 30 years, and it's about 300,000 hectares, and it's characterized by the rule of law, not the rule of science. So it's sort of awkward.
Yeah.
Because in reality, at the flip of a switch, they go from 2 stories to 55 stories. There's no conceptualization of anything. It's covered under the Planning Act, the official plan, the zoning bylaw. They're all molten and stuff. So what I'm trying to say in plain language is there's a real challenge to be able to sort of conceptualize this kind of approach, but to make it real where you live. You know, so there's sort of an interface between what would be good science or something. So for example, the city of Ottawa started its climate change in 1992. And now it's 2017 and we have no data. So I'm not sure where you go from that. I mean, Ontario had 2 stations at one point, but I mean, you know, if you look at the city, like an expansion of the airport parkway, it's 500 pages of environmental assessment, but again, there's no serious data. I mean, it's uncontested politically,
Yeah.
but I'm just trying to say it's very hard to take these ideas and to dock anywhere with them in the world of, you know, Ontario, say. So when you say you work abroad, that's, to me, is code for other consultants that I've known that have had similar situations. They're not nearly as well, they should be engaged where they live, as well as Australia or Germany, it doesn't matter. But it's not so easy, so, you know.
Well, to be frank, it's just we don't know how to do things very
Yeah.
efficiently anymore.
Yeah,
We don't know how to build projects or,
yeah.
you know, and it's funny because we're so concerned, we seem to be so concerned about doing like all these assessments and stuff, but in the end, a lot of the stuff just goes through anyway. It just takes a long more time.
The assessment process is a sign-off.
Yeah.
It's not an assessment of the environment. These are class environmental assessments. They hire the consultants, they sign it off. That's the
Yeah.
way it works. So the city planning projects 250,000 people by the year 2036. And the result of that is homes and building sites. That's it. So there's no water, oxygen, energy. So the problem is that the interface, successfully, in theory, has to be through the architecture, which is kind of awkward because I'm more at the, how does the planet work? Like I came from the biodiversity side, so I'm more on the energy profiling and stuff. That's where you're really talking to me.
Mm-hmm.
I'm struggling to be able, it's like I need to make my own government, doesn't make sense.
Well, it would be an improvement.
It would be an improvement, but it's you know. So it's, you know, looking at temperatures and wind velocity and stuff like that all makes sense to me pre-buildings.
Yeah.
Well, once you have 60,000 buildings, you're into an applied situation already, and you're adding more buildings too. It's not wrong. In fact, it has to be if we're adding those people.
I think.
So I'm sorry, it's sort of a comment, but it's very interesting. I wish I could use it more.
Yeah, I think in the States is a little bit better, I think, than we are. They're building a lot more inventories.
Yeah.
So there's requirements to, if you're of a certain size, that you have to be contributing, say, your energy usage to a large database, and that's GIS, so people can extract information citywide energy usage for extended period of time, and that's quite interesting. I don't know again, I don't work enough here to know what happens in Ottawa, if there's any kind of what the GIS capabilities of Ottawa are, other than if it's just the land, outlines of the land, everybody's plot of land. That's the bare minimum, right? But sometimes there's more.
Quite a lot. I mean, there's quite a lot of data there, but it's not relevant.
Yeah, yeah.
I mean, what's relevant is, you know, ambient temperature, forest at noon is minus 20 degrees
Mm-hmm.
compared to asphalt. I can show that study,
Mm-hmm.
but when you go up against the law, they have no references. You understand? They have
Yeah,
power.
yeah.
That's different.
Yeah.
It's not saying, there's my hand. Whenever I've appealed to the courts, I have my hand is open. I have all the references that I've used. They have law. It's not.
Well, we've had chats, I can't say too much about it, but we've had talks with some people, like some large software companies that are doing developments, and I can't say too much about that, but the idea of taking a large portion of a city, censoring it up, and making the data available to the citizens. So what is the temperature going?
But then, with due respect, you're in the same situation as why doesn't the government do that? Why do the citizens have to do that? It's sort of awkward.
Well, the government does it indirectly because they fund everything.
They find.
Everything just gets funneled to the corporations. I wouldn't get political. I'm not going to get political.
No, I heard that. So I have a kind of a trick question.
Yeah.
So Dr. Epsimon heats the planet, right?
Okay.
I mean, he does.
Oh, with his computers?
I mean,
Or does he have a lot of computers?
I've known him for decades.
He was in my undergraduate class 50 years ago.
Ah,
So
50 years ago.
it's true, pre-electricity. There were 3 buildings here. So, but it is true, mean temperature, as a species, we actually heat the planet.
Sure.
I mean, sort of, it's kind of curious, because there are millions of species that don't heat the planet, but overall, because we maintain a temperature,
Yeah,
we actually heat the planet ourselves.
right.
I mean, that's a starting place. You know, it's you need the forest to keep the planet cool. I mean, it's
Yeah.
to prove it
Yeah.
requires data, it requires philosophy, etc. You know, it's interesting.
Yeah, I think our heat output's probably fairly insignificant relative to all the other
I'm on your
processes.
side.
Yeah,
Just being
but
setting it up.
yeah, more the data. I thought you had a lot of computers or something. That's why you're pointing at like
Oh no,
data centers
I'm
and things.
pointing at him. It's, you know, he doesn't have his fencing material here with him, but we're old enough now that we can be playful.
So, given that we have a pretty diverse audience here, and that I'm super happy actually about the big participation during the talk, after the talk.
Yeah.
I don't know, who would like to run away and who would like to stay and discuss more, because you still have a little bit of time. I think
Sure.
the room is booked for another half hour. What I would like to do is to have an official thank you to you
Oh, you're welcome.
for giving the talk, for engaging everyone, to give the people who would like to leave the chance to leave without seeming impolite, and still to invite everyone else to stay here for a few more minutes. Have a cookie, have a piece of coffee, continue the discussion if you like, if that's okay with you.
Oh yeah.
So for the moment, just as the official thank you, let's have a round of applause. Thank you very much.